So now that we've seen a little bit about how this process of antiderivatives work, and that we're really just going to be looking at a bunch of derivative rules in a backwards direction, we can take a look here and start to summarize some derivative rules in reverse from some of the more complicated derivatives. So let's take a look here at this opening theorem. If f and g, capital F and capital G, are antiderivatives of little f and little g, respectively, then we could definitely state the following. C times capital F is an antiderivative of little c times f of x. Notice if this is my answer, this would kind of be the question. Notice the derivative of this would produce this. This is just our constant multiple rule, kind of acting in reverse. So if I ever saw a constant times a function, and I was taking a derivative, I know to leave the constant alone and just take the derivative of the function. But this actually works now in the opposite direction. If I ever saw a derivative and I was working to undo it and there was a constant in the front, I can just take the constant away and work with the antiderivative of just the function. In a very similar way, I can see that if I have f of x plus or minus g of x, this is an antiderivative of little f of x plus or minus little g of x. So this is essentially my sum and difference rule being worked in a backwards direction. Now I can see kind of how this comes into play by taking a look here at something like example number 3. So here I'm going to be interested in finding the most general antiderivative of my function f of x. So that is, I'm looking for capital F. And so I can essentially look to do an antiderivative of each of the individual pieces here because I know that my sum and difference rules can kind of be applied in a reverse order. Whatever my function is here should probably have some shape generally that looks like this. Something minus something plus something, because I know when I take the derivative of this, I would do the derivative one at a time and hopefully generate each of these three things. So if I can figure out what each of those things are, I'm going to be in business. Now, I can see here that when I do my antiderivative of my first piece, I can kind of ignore the 6 and just focus on my antiderivative of x to the second power. That's kind of using, again, my constant multiple rule in reverse. I could see that to do that, I can think about undoing a power rule. I could add 1 back onto the power, so when I take the derivative, I'll go back down to power 2. But then I'll put a 1/3 in the front, so that way when the 3 comes down, I cancel it out immediately. I can do the same thing over here. I could ignore the 2 and do an x squared with a 1/2 in the front. Or I could have just noticed that this here is exactly just the derivative of x squared, and I wouldn't need to do this 2 times a half, which is going to cancel out anyways. The last thing that I would have here is, well, where does 1 come from? What could I take the derivative of that generates just the value 1? And well, an easy answer for that would just be the value of x. Of course, then I could write here plus c to make it as general as possible. Now, of course, I could simplify a little bit more after this. 6 times 1/3 is going to create a value of 2. 2 times a half is just going to create the value of 1. And so here is an antiderivative. Again, I can easily check my work by just taking the derivative of this function and seeing if I do indeed get back to where I started. All right, so let's take a look here at one more. I want to find the most general antiderivative of this function here. It's g prime, and so when I go a step back up, I'm going to be attempting to find just g itself. That's what I'm going to be looking for. What does g of x equal? Now, I can see that, again, I can take the antiderivative of each individual term here. And the first term really isn't that bad. I know that I'm going to have, I'm going to have to figure out where 4 cosine would come from. So I can leave the 4 alone and just think about what could I take the derivative of so I get the answer of cosine. So thinking about my derivative rules, how about the sine function? That would work perfectly. But here's where I'll notice a problem. When I look at the second term, is this any derivative rule that you've memorized? Like, do you remember a derivative rule that gave you 2x to the 5th minus square root of x over x? No? I definitely don't remember anything like that. That looks really messy. And so what we're going to find is that when I'm doing antiderivatives, sometimes it is helpful to use algebra to rewrite our function before we find antiderivatives. Because notice here, if I was to go ahead and rewrite g prime of x, I could see that the reason I'm doing this is not because of the first term, because that was easy to find an antiderivative of, but maybe I could find a way to rewrite the second term. Now here's one way that this might be easy to rewrite. What if I took this and I wrote it, instead of as one fraction, as two separate fractions, right? Like I expressed it like this. Because then notice that each individual fraction could be simplified a little bit. My first fraction could be written as really just 2 times x to the fourth, removing an x from top and bottom. And over here, I could actually rewrite this as 1 over the square root of x, or x to the negative 1/2. And so I'm going to work with this final form here to try to go ahead and find my antiderivative. So I already have the first term down, but let's focus on the next term. I know I can leave the 2 off to the side, and I'll add 1 to the power, divide by the new power. I can actually do the exact same thing over here. I'll just leave again that minus off to the side, and I'll add 1 back onto the power. Notice that would bring my power back up to the value of 1/2. But notice that when I take the derivative here, this 1/2 is going to come down. And so I want to kind of catch the 1/2 and cancel it out immediately, because I don't want a 1/2 sitting in front. So what could cancel out a 1/2? Well, how about a 2? And then, of course, I could write plus c. So if I wanted to write this as cleanly looking as possible, I could say this is 4 sine of x plus 2/5 x to the 5th minus, and I can even write this as a 2 square root of x plus a c. There it is. So this is really, really useful to note that sometimes when I see things that don't look like derivative rules that I've memorized, it's very useful to try to go ahead and rewrite what I've been given. Just use some basic algebra, try to rewrite my derivative first, so that way finding the antiderivative is a little bit simpler.